Cool. Yeah, Jose kind of talked about it. It's just well, we're gonna take it to the power of 10 again. I mean, here's the n, right? This is, let's say this is our 11.5. Well, now it's gonna be positive 11. No, now it's gonna be positive 12 actually, because we round it down to 12. Well, negative 12, and it becomes positive 12 because we take the absolute value. And then down here's the last line. Tolerant is, we're gonna take to the power of 10 again. This is the reason why we had to like do all this sort of funny business over here is because of this rounding part, this floor. So we kind of take the next power of 10 down. So in that case, it's going to be like 10 to the power of, well, now it's going to be like 12 n minus 1. So 10 to the power of negative 11. So one decimal place fewer than the difference. One decimal place fewer. So we'll take like the difference, the order of magnitude of the difference. So like order of mag of diff. That's this thing right here. And then we'll take the next higher as the tolerance.
Dennis, just a quick question.
Yeah.
Who wanted to go into the breakout room?
Yeah, you guys. Yeah, Michelle and you. Unless Michelle didn't have a question anymore. Can you do that? Or like, can you?
Yeah, I'm just not finding.
I think it's under more. I think join breakout room. Like both of you guys can do that.
Okay. Thank you.
Yeah, let me know if you have questions on that. I mean, this is a relatively short problem, I think, in terms of like what it's trying to do. I'm open to any questions regarding this. Floating point numbers are just like, it's weird. It's just because like computers think about numbers differently than we do. You know, we're used to thinking, oh, like this has like this number of decimal points, but like it's because of the binary mind of computers. It's like they use base 2. That's all this is. A lot of this lab is like, oh, understanding that computers think in base 2. Okay, let's see here. Oh, wait, the left?
Yeah, I think she might have left.
And let me check the participants. Hold on. Oh, I see. Okay.
Okay, then never mind.
We can, yeah. Okay. I'm going to let people screenshot this for a second before we move on to the next question, unless some people have stuff they want to ask about this. We'll go to 4 next, I believe. 5, 4, clearing in 2, 1. Clearing all drawings. Oh, someone in the chat. There's 2 parts of part 2. Oh, my mistake. So compare floats was the first part. Let's see what the next one was. Not in lab 3, lab 5.
Oh, the binary representation.
Binary, okay. Floating point numbers in binary format. Okay, let me open that up. Where was it? Lab 5 solutions. Binary tree complement game. Oh, single decimal. Okay. Oh, okay, it was deceptively short. Oh, no, it's deceptively long. Because it's long, but it's deceptive. All right, what are they doing here? So with actually, let me stop the share for a moment. I'll come back to this, and I'll like share the PDF. 3, 2, and 1. Okay, so binary representation of floating point numbers. So you have a binary input, and then we're representing that by a result. So this is going to be like a big old number, like, so it's a character, by the way, not a double. So 1 0 0 1 0 0 0 0. there's going to be 32 of those. So it's going to be a 3. I forget. There's like half. There was like the single, double precision. I think this is single. Let's see.
Let me see.
Single
9
precision.
single to decimal.
Yeah, single
character.
precision. Yeah, and then 64 is double precision. So yeah, we're going to code this. And let me scroll down a little bit. So, okay, it gives you the equations. So this is like the different conditions for like whatever your exponent is. There's like different cases. They gave you like an equation in lecture, I believe, that like only applied to some cases. I think it's this one. That's like, it's if you're, yeah, a lot of this is just like applying the equation. So you'll have different, there's like 3 different regions for this. You'll have like the sine, you'll have one of them that's like -1 to the power of like whatever that first bit is. If that's 1, then it's like a negative number. If it's a 0, then it's a positive number. That's the idea. There's this part, which is like 2 to the power of, so it's, let's see. 2 to the power of, and the e is the, so you'll have like 9, that's 9 minus 2 minus 1, which is 8. So there's 8 of these. So it's like there's one bit, let's say like that's 0. I'll write a box for this one. And then there's another one. Actually, no, well, instead of doing this, what am I doing? Let me stop sharing. I have something to show you guys. I showed this during lecture a while back, by the way. Well, not like during lecture, but I posted in the chat. Float toy, where's this one? There we go. So it's single precision, so we'll use the one that's like halfway down here. Where is float toy? Here it is. Float toy. You can look this up. It's just called like float toy. You look it up. And then you can like play around with this. Okay, I'll just click and drag. Nope. You make all these 0. No, I want all these to be 0. Hold on. Play around with it to kind of see how this intuitively works. So like this is 1. You can make it 1 to make it -1. There's 8 of these, and these control like the power of 2. Like if we make this all like this is for like positive numbers. Notice that like this is infinity if you have like all of them 1s, but otherwise you have like 2 to the power of 121, to the power of like each of these is a power of 2 basically. So let's see how this works. So let's just put a 1 here. And then each of these is like, this is 2 to the power of 2, 2 to the power of 4, 2 to the power of 8. So like the thing about this is that you have like you add whatever this is, it's a weird thing where like you add this to the exponent. It's not like you multiply it by that. It's like you notice that this is like this was -120, right? If I do this one, this 27 here represents 2 to the power of, I'll annotate while I do this. So this is like annotate, come on, there we go. 2 to the power of 8. So if I click this one using my mouse, it'll be 2 to the power of -112. So it's like if you had 2 to the power of 2 to the power of, wait a minute, no, sorry. This is not 2 to the power of 8, 2 to the power of 3.
Yeah.
2 to the power of 3 minus d, where d is like the bias. You'll notice this is like a negative number, right? It starts off at like -127 or something like that. Since I have like all of these 1s, it's like 2 to the power of 3. So I'll write it over here. 2 to the power of 3 plus 2 to the power of 2 plus 2 to the power of 1. Let me see if I got, so 8, 4, 2, that's 6 plus 8 is 14, 14 plus, okay, plus 2 to the power of 0. And that's 1. All of that minus 127. And I believe that gives me -1. Yeah. You can check my math on that. And then, I mean, we can keep going if we wanted to. This is -96. So this should be 2 to the power of 4 next. So that's 16. 16. So 96 plus 16 is 112. Yeah. Okay. So these are like, I mean, you can confirm this by verifying with the equations. It's like the powers of 2. Powers of 2. Of 2. That's like the E. And it's minus the D, which is like the bias. And like there's a reason for this. Good.
Oh, sorry. I was just gonna say, so this combination of powers of 2 that Dennis just showed, the 2 to the 3 plus 2 to the 2 plus 2 to the 1 plus 2 to the 0 minus minus whatever the bias is. This is what the computer uses to be able to represent very small decimals. Yes, so it allocates a portion. So it has, by the way, I don't know where I got the 16-bit number from. I got myself mixed up. It's either 32 or 64 bits for a number. That depends on the type of number that you're using and the processor that you have, the type of processor that you have. I think most modern computers are 64 bits nowadays. But this has to do on what the physical process is within the computer. Remember that computers are actually a physical thing, and there are physical phenomena going on inside. So let me annotate this. Where is my annotation tool? No, I don't want to share my screen. I want to annotate. Okay, I lost my annotation tool. This is embarrassing. Where on earth can this be? Sorry, Dennis, go on while I try to find my tools.
Okay. I can move on to the fraction, what that kind of does. So, by the way, this whole time I'm talking about the general case where, so you have like 1 plus f. And so this region over here, it kind of starts off as, where is it? Stop annotating, and I'll click this one. Let's see what happens. 1.5. So this first one over here, this first box is 2 to the power of -1, which is 1/2. So that's 1 plus 1/2 is 1.5. You'll see that over there. You keep making these, so that's, you add in a fourth, which is 2 to the power of 2, etc., 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 etc. And that's like the first 2. You can kind of see it tending towards 2, right? You get the point. But it tends towards 2. So this whole number right here is like between 1.5 and like 2 in the general case. And there's like other like cases where like, oh, what if this is all 0? Because like, oh, this is 2 to the power of -126, but there's no, like, why is that? Why is it -127? But like, that's because it's a weird case. It's like in the, what's it called? It's like, well, yeah, you'll see in the PDF where you'll have, like, if E is equal to 0 and F is not equal to 0, like E and F are just the green and the red regions you see here. So I can label this as, I don't want to spend too much time on this, but like this is the idea behind the floating point numbers. E and then F.
So I'm a little confused by F. So why would the more you add to, so when you add more like F to so like at 0.1, what is that? Is that F to the -1 or
F to the, so you're oh, sorry, this is like
no.
2 plus, you're adding it on, you're not like multiplying it.
okay.
It's just like this. So 1 plus 2 to the power of, and like let's write this in terms that like we're more familiar with. 1/2, 1/4, 1/8. That's why it tends towards 2. It's again, not really infinite sum, but like it's a long sum. Powers of 2. This takes a while to kind of grasp. I speak from personal experience. Okay, go ahead.
This is a really cool tool. You guys should play with this. What I was trying to say before is that this is related to how the computer physically processes information. And what goes on inside a computer is that you actually have a core within your processor that's geared such that it has 64. I think the term is register, but basically it has 64 slots or transistors in here where it can store basically 64 bits at a time at once. So whenever a computer does whatever algorithm you told it to do, it can only perform a series of very simple tasks really fast. So it basically takes one number, then sends this to some black box, some tool within the processor that it gives a previous number plus something or times something or minus something, and then the output goes back and is stored in here. So it has to be very efficient on its use of memory because it only has 64 slots at one single time. So what it does is allocating the first of these slots will tell me the sign. Dennis had already wrote this here. These guys will tell me the scale, and these guys will basically tell me the number, basically. So this is a very interesting thing to analyze how computers actually work physically. And if you guys are curious at any moment on this topic, I do recommend a book called How Doth It Know? So that's a short book, that's a short lecture. I do recommend that on your free time if you're curious. It basically goes from scratch all the way to the end on how a computer physically works. It's a very interesting subject, and this is something that you usually don't think when you're programming, but in some cases this becomes an issue because of this precision that we've been talking about. That's some really small numbers and some really big numbers. The computer cannot tell the difference between within a range. That leads to numerical instability. So this is something to bear in mind when you're working with extreme cases. Sometimes your code doesn't work or blows up when it mathematically shouldn't, but you're actually reaching the physical limitations of your computer. So that's a very interesting problem to run into. Anyways, that was a tangent, so sorry about that. We should go back to the problem. Let me clear all drawings.
Oh, should I go back?
Yeah.
All right, stop share. Float tool I highly recommend. Oh, we have a half an hour left, so let's speed things up.
Oh yeah.
Okay, sharing MATLAB in 5 seconds. Are we still recording? We are. Let's see. MATLAB. Okay, single to decimal. Okay, it kind of breaks up the code for you as well. So you start the binary, this big old number, 1, 0, 0, 0, da, 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 da. So remember, sine 2 to the power of exponent minus the bias, and then 1 plus f. In the general case, I mean, here's the cases down here. I mean, like this if-else tree, that's just like those 5 cases. Like E not equals 0, E not equals 0, dot, 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 dot. That's this stuff down here, what that's programming. And I can, wait, let me see if I can scroll down and then capture everything. Okay, it's just like a bunch of ends at the end, so yeah. Okay, this is the meat of the problem. Okay.
And again, if you look at lines 10 through 13, those are selecting which part of the binary, of the huge binary number represents what. So the first number, the first element represents S, then the next 8 bits represent E, and F are the last. Is it 32? 22 bits.
23.
And then it's just applying. Oh yeah, 23 bits. And then it just applies the formula.
Okay, anything tricky that we need to worry about in this one? Okay, here's the bias. That's this D over here. That's the reason we had like those big old negative numbers in that float toy. S, no.
So just as something to think about when we were looking at the when we were talking about really huge integers that the computer would not be able to represent. If you look into wait, let me get the annotation tool. If you paid attention in the tool that Denise was showing, let me change color. This part got to be up to 2 to the 1. Was it 2 to the 1 or 2 to 0? I think it's 2 to the 1. So if we have here 23 bits, then the maximum integer that we can represent would be something like 2 to the 24 plus 2 to the 23 plus 2 to the 22 all the way to the 0. And if we do that plus 1, the computer will take that as 2 to the 24 plus 2 to the 23. So it will not be able to see the difference. Plus 1 or plus 5. The computer cannot tell the difference between one integer and the other after that.
I was kind of considering, by the way, going back to the float toy and just like kind of plugging different cases and seeing each of these like 1, 2, 3, 4, 5 at work. I'm not sure we'll have time to though. Maybe if we have more time on Wednesday, we can try doing that because we already showed the solution, so we can just like explore it more depth. Maybe just like a brief thing on Wednesday.
In the debugging mode.
Oh, not in debugging mode, just like literally have the float toy and side by side with this. Like try making all of these ones 0, have all of these ones 0, that kind of thing.
Oh yeah, and that's also a good way to test your code.
Some people are telling me to scroll down. There's nothing below this. It's just a couple ends like this. Literally just if you can put enough ends, it's just, yeah.
Okay, should we try to go into problem 4 or?
Yes, let's. I'll clear drawings in 10 seconds. 9, 5, 4, 3, 2, and 1. think I actually wrote too much substantial. All of it's in the IE, like the problem statement. Anyway, stop share and then let's go back to the PDF. Where are we looking? Problem 4. Find the nth largest element. That's binary tree. Okay. Share screen and lab 5. All right, binary tree. What do we have here? Just a random unsorted array as the input, and we want to spit out 2 things: a tree like 1, I assume like 1, 5, 3, 2, ... containing the numbers in the given array.
Left child, value, and right child. And then the depth is the depth of your binary tree. Okay.
What does this look like? Ooh, interesting. So take it and then store it in a binary tree. Show the value that's greater than. To balance the tree, there's an even number of nodes. Oh, wow. There's no sort rows, no median. Okay, see the tester script for an example input and output. I mean, here's one. So it looks like you're trying to like make the tree as like evenly distributed as possible. You don't want this to like have one really abnormally large branch. So for this one, they chose like basically the median value. Like they kind of do it like this down here. They picked 3 because it's like if you sorted it out, it becomes annotate 1, 3, 8, 10. So then you can pull this one out as the let's be smart about this. 3 as the median number, and they chose the small one arbitrarily. So 1 and 8 they chose. So it's like the next one's out. Wait. No. It's not necessarily the next one's out. It's you kind of create 2 different ones. You select the 3, you pull it out, and then you make 2 smaller arrays out of that one, and then you pick the median out of that one. So like here it would be smaller, 8, 10, like that. And if they're bigger, you need to you'd split it into if you have 1, 2, 3, and that were it, and then 4 becomes like your center, your origin point. That's 4, and then you have 5, 6, 7. Obviously, this is sorted just for ease. Then you pull the median out of this one, and you do 2, then 6, and then these become like the parent of the 2 children, 5 and 7. That's what I think they're going for.
And the goal of this is to sort whatever inputs you got. So let me annotate this in green is fine. So at the end of this example, you will end up with the series of numbers 1, 2, 3 from this guy, this guy, this guy, 4, 5, 6, 7. So here the input would have been what Dennis had shown here. Let's say this one is 4, and which one am I missing? 6
and 7.
And 7. So anyone has any questions on the broad aspect of the algorithm? You take the middle one, and you have the group of numbers that are smaller than the median and greater than the median. Then of those 2 groups, again, you take the median, you divide them into smaller and bigger, and you do that until you have a single number on each side. And once you've done that, you have the number sorted out from smaller to bigger.
Right. I think part of this is you can't use the median function. You have to find a way to take the median out of an unsorted array. So
You
I think
cannot
we
use the
can
median
clear
function?
drawings and 10, 9, 5, 4, 3, 2, 1. Let's go to MATLAB and see how they do it in the solutions. Binary. Huh, there's like a binary tree and a binary tree original. Let's go to the original, I guess. I mean, no, the one that's not the original, I mean. Oh, interesting. Okay, so yeah, they. Oh, I can. No, you guys can't see. Now you can see. Right now. Okay, here it is. My binary tree. They do have a function for taking the median, which is smart. And make sure to subfunction. Take an array, return the median, return the location of that median. I guess we'll just start with this one. We'll start from the bottom.
Yeah, that's good.
See how this works. We have an array. We'll assign that to A1. Why they use A1? Well, because there's another A2 that's going to be later on. Let's see 2, 3, 1. Let's use an easy example. Z, that's going to be 3. A2 is 0s, 1, comma, Z. So that's going to be like just 0, 0, 0. For J in 1 to Z. Okay, so we'll loop over the array. So A, comma, B. So maximum of array. So this one is going to return the maximum. So this is going to be 3, and this is going to be where that is. In this case, it's going to be 2. 3 at position 2.
So remember that syntax of the outputs, or the order of the outputs, equals the maximum and its index. So this is what they call A, this is what they call B.
So what are we doing here? Array B, thank you, Jose. Then that's basically going to nix out this part. So 2, 1, it collapses in on itself because it's empty. It's no dimensions. And A2J, that's this one right here, is equal to A. So that's just going to be 3. So now we take this one and this one. I'll erase this just for clearer flow. 2, 1, and this one's going to be 0. I think that's right. The maximum of array. Hold on a second. So we're looping over this. A comma B, array B, AJ. No, wait, this is.
Yeah, A2J equals the.
There we go. That looks better. So this is 3 now.
Yeah, J equals 1 right now.
And this becomes. You'll loop over this, and this will become 3, 2, and then 1. So this basically like sorts it backwards. But it doesn't matter, it's just median. So what does this do? So T Z plus 1 over 2. The length of it plus 1 over 2. So that becomes T equals 4 over, that's 2. MD, the minimum, oh, here's the ceiling of floor functions again. We have the minimum of A2 ceiling and floor of T. So T, this is 2. We don't really need the ceiling and floor here. We'll need it if this were like 3. No, if this were like 2.5. Like let's say this were 2.5. Then we would have like 2 and 3 as the floor and the ceiling respectively. And then it'll just take the median of that. But yeah, the minimum of that. But in this case, we don't need to worry about that. Both these are 2. This is just 2. Therefore, the minimum is 2. And MD is also 2. So the index, last line here, index find the location of where, so the first time when A naught, let's see, where is A1? Where is A1? The array. See, the original array, index equals where, let's see. Find 231 equals MD, and that's 2. That's this one. All right. So the first time that happens is 1, and that's the index. So it's located at position 1. The median is at position 1, and MD is 2. So A2C.
So just a few points of clarification for these two guys here. What they are doing is that if I have my A2, actually you have A2 down here already. If I have my A2, which is the sorted array from biggest to smallest, then I look at the length plus 1 over 2. So that will be either the middle position, or if it's like an even number, like if this was 4, 3, 2, 1, then it will be like 2.5. So this guy tries to get to the middle position, and these guys look at the case. So if this is an integer, if this guy is an integer, because if you have an odd number of elements, this will be an integer. If this is an even, then this is not an integer. So in the case that it is not an integer, this guy, the ceiling looks at this element, and the floor looks at this element, and you want the smallest of those two elements, so it picks this one. In our example, you have an odd number of elements, so you'll just pick the middle one. Yeah, so these two are trying to pick the median. And in the next one, the find function will take an array of booleans. So in this case, as Dennis wrote down here, we will have 231, which is our original array. So 231, and compare it to the median that we found before, which is 2, the guy we found here in line 47. So this will compare array 231 equals to 2. It'll give it a set of booleans, true, false, false, and find will give the index of the ones that are true. So that's why this gives us 1. If we had an array that, if we had find of false, true, this will give us something like 2 and 4. Yeah, find searches for the positions of the true values. In case you guys are not familiar with any of those, or if lines 46 and 47 look kind of sketchy, that's what they are trying to do.
Thanks, Jose. And one thing that I try to do when I'm trying to understand more complicated stuff like this, is just plug in numbers, plug in like test cases, and then see what the patterns are. What is this code doing to my input? Essentially, we're just building machines. It takes something in and it spits something out.
And when I'm trying to code this myself, like from scratch, here we are looking at someone else's code and trying to figure out what they're doing. So plugging numbers for a small example, that's a good idea. It is also a good idea when you're trying to build it from scratch. When you look at yourself, when you find yourself in the scenario where you're oh, sorry, this is the wrong tool. When you have some vector v of some dimension, so this could have 3 elements or 16 elements. And you don't know, this has the ability to have a range of dimensions, and you want to pick the middle value. So I would also plug in numbers for simple scenarios. So I would look at B has dimension of 3 already, like this. So 1, 2, 3. So I want the index 2 for V equals 4, dimension of 4, 1, 2, 3, 4. I want to pick somewhere in here, so probably 2.5. So this means 2 or 3. For 5, this equals to 1, 2, 3, 4. I want my function to extract the third index. So I would look at the pattern. This has a length of 3, length of 4, length of 5. So if I want to get from 3 or from 5 to these outputs, I would try 3 plus 1 over 2. That will give me 2. 5 plus 1 over 2. That would give me 3. And that's how they get to a function like this one. In this case, this one's a little bit tricky because 4 plus 1 over 2, that gives me 2.5. And I see that 2.5 is not really a valid index. So that's when they go to the next line and check the index right before and the index right after. So in a general scenario, try to think on the simplest example you can and try to write down numbers, like in a notepad or whatever. And that's easy. That way it's easier for you to find patterns that you can actually code into a computer.
So let me ask you a question. Do you think on line 47, the minimum of ceiling and floor is necessary? Could we just write A2 floor? Actually, no. Oh, never mind. Yeah, okay, why do we need that minimum there? If we have ceiling and floor.
There's actually in the PDF, there's a condition that tells you, let me read it to you. You want to separate the numbers into the left child and the right child. So that it says that the left children are placed so that the left child of each node has a value that is less than or equal to the current node.
I guess what I'm asking is like this line right here, this A2 ceiling, A2 floor, it takes like the middle two of that array, right? Like let's say it's like 6 and 7. I guess I'm just kind of like,
I see what you're saying, because it's sorted from bigger to smallest, so the smallest will always be the one on the right, right?
It's like, so it's,
we could just pick
yeah.
ceiling.
So then it's, let's see,
I think we could
do it this way for like just if you're in doubt, but I'm wondering whether that's necessary. If just the fact that we're using A2.
Yeah, because A2 will always have the format of let's say A2 equals 8, 7, 5, 4, 4, 1. So are these even? Yeah. So this looks at these two numbers, and by definition, this one will be the smallest one. So I would actually just use ceiling.
Don't do that if you're not confident, though. Understand what that's doing, and if you're confident, do that. I personally am not. I would need to like test this to make sure that That's a good idea. I think that's right though. There might be like a subtle thing that I'm missing. Okay.
Yeah.
We have
yeah,
10
me
minutes
too.
left.
I don't see it.
We have 10
Yeah.
minutes left. Should we? Let's
go
roll
ahead.
up. All right. Stopping in 5, 4, 3, 2, 1. Clearing all drawings. Let's scroll up. Let's hopefully fit all of this in the same one. Let's
Almost.
see. Oh, we can fit in 2. All right, so then this is like the rest of it down here, just barely. Okay, so we have something that takes the medium. So now that's squared away. That's going to be very useful. So treacle cell, so we're initializing here. Always a good thing to do. Well, not always, but in this case, in a lot of cases that we've done. If
Almost
it's
always, actually.
Huh?
Almost always, actually.
If we have a like a loop, yeah.
Yeah.
So we have this one. Before we do anything, we just kind of say, hey, this is if length of array is equal to 1, so then it's just we don't have any parent or we don't have any children. We're just yeah, that's not yeah. We just have an array. Is empty. So if it's empty, then we just do. This is like I'll just draw this out. So let's say our array is like 1. Then we just don't have anything else. Nan and nan. Otherwise, we just have nan. That's this case. It's depthless.
And the depth is just one depth of the tree before you get to nans, and here there's no depth.
Yeah. My median array. Yeah. So otherwise, this is the main case. We have so here's my median function. First of all, we want to get that median out. Let's say that's 3. So the array of that index is going to be, let's see. Okay, here's just initialization. And then here's what we were talking about before regarding splitting it into a low vector and a high vector. Here's everything below that, 1, 2, let's say. Here's everything above that, 4 and 5. And this is not necessarily in this order. Let's say this. So here's the low vector, LV, here's the high vector. I want to use Jose's for practice. Oh, well, yeah, this is same numbers. Yeah, this one will be you'll take this one out, and then you'll take, oh, this is low vector. Hold on, let's see. If it's unsorted, then we'll say, so the array at that index where the median is will nix this one out. The low vector is going to be whatever the low vector is. This is going to be like empty when it first starts out, this low vector and the high vector. So we'll do that.
Just to clarify, what Dennis said is that here array will be equal to 2, 4, 1, 5. It just scratches that index out.
So I'll put this in a cloud over here. So if we have 2, 4, 1, 5, then we'll loop through this and then we'll say, okay, where do you go? This is a sorting hat. This is low vector. Okay, are you less than the median? Okay, you go over here, Hufflepuff. 2, 1. Here is 4 and 5. Sorted. All right. Let's see. Okay, probably need to. Now we'll try leaving this up. We'll move up a little bit. This is gonna be slightly off, but that's fine. Let me erase like part of it.
Or let me see if I can move it around while you go ahead.
Sure. Didn't know you could do that. Okay. After you do that low and high vector, after you've created that, and by the way, you'll do this for like repeatedly. So you'll initialize for the different depths, right? And then you'll have So here's, okay, remember what I said about, like, here's the thing about recursion, right? When you have like a branching problem like this, think recursion. You'll read, this is your new tree, your low and high vector. You're gonna, like, now the very first branch of the tree was, it started at 3. Now you'll have like one of these children becoming the parent. Let's say like 1 and 4. And then that'll have maybe more children branching off of that. And you'll do that for, like, the process repeats itself. If you want to do it with the vector on the bottom, the vector on top. D1 and D2, let's see what this one does. Or D1 and D2. So you'll want to assign these values to whatever the indexes of these outputs are. Wait, let me see if I'm getting this right. Whatever the, oh no, that's just a depth. Sorry, that's not an index. Well, let me check the chat. Let's see. Jose, can you help Jared? He has a question about number 1.
Okay.
Or unless he prefers me, because I'm screen sharing right now.
Let me move to a breakout room. Also, I didn't find out how to move those guys, so you can go ahead and erase them.
I think they just joined the room.
They did? Okay. Let me.
Okay, so where was it? Tree 1. So after you finish running it through this, right? This is a recurring relationship. This continues until the entire tree is filled. So it goes like into that. This is the whole inception sort of thing, and then it goes back and it returns these outputs. So this is like the entire recursion right here. May not look like much, but these 2 lines do a lot. So this over here, this is just the cell array. It's just here's the elements of the cell array. This is so parent, and then the 2 children, CH. This depth counter right here, think back to your MyNight problem. During the MyNight problem, you had like a turns equals turns plus 1 or something like that. Or whatever it's called. It's like on the bottom, it has like a something plus something equals something plus 1. That's how you count like the number of moves. It's like that, where you had like the MyNight starting here and it moved like all sorts of places here and then moved somewhere else. The MyNight problem, MK MyNight 2. It's like this, but instead of counting moves, you're counting the depth of the tree. And your depth is like the maximum of the 2 depths. It's a recursion problem. There's similarities between this and what you're doing for the MyNight problem. So if conceptually you're having trouble with this, think back to that. If you're looking for the solution for that, I believe he gave the solution out for that in Wednesday's lab of last week. So don't remember what day, like the 30th, I believe. Yeah, I think it was September 30th. So like 50 minutes into that, they show the solution. 53, I forget the exact number. Okay. Just about done with this one. Does anyone, like, we can scroll up, scroll down as needed, but it's 8 o'clock right now. We'll do some more. I think we've only used up 2 of these, so like work through it, and then we'll see what people find tricky, and then we'll do like that final solution on Wednesday, and we can re-show some of these as needed. But it is 8 o'clock. You guys can go. I'll stop the recording.